Hey everyone, and welcome to AirWise Academy, your trusted source for EASA Part-66 learning. In this session, we are turning our attention to Submodule 4, Optics, Light. Our journey will take us from the fundamental behavior of light to its advanced applications in modern aircraft. We'll start by exploring the fundamental principles. We'll investigate the nature of light itself, then see how it behaves when it bounces off a surface in reflection and bends when passing through materials in refraction. In the second part, we'll apply these principles to optical components and systems. We will see how lenses manipulate light to create images. Then we will dive deep into the technology of fiber optics, covering essential topics like its cable construction, the different fiber modes, the critical techniques of termination and splicing, and finally, how it all comes together in a fiber optic data link. Understanding these concepts is crucial for working with the sophisticated communication and sensor systems in modern aviation. This knowledge is required for both B1 and B2 certification levels. So, without further ado, let's shed some light on the subject.
First, light is not something unique. It is a specific type of electromagnetic radiation. It's part of a vast, continuous range of energy that surrounds us, known as the electromagnetic spectrum. The light our eyes can detect, visible light, is just a tiny slice of that entire spectrum, as you can see referenced here in the figure. Now, light behaves as a wave, and a key characteristic of any wave is its speed. In a perfect vacuum, light travels at an incredible constant speed, denoted by c, which is approximately 300 million meters per second. However, when light passes through any material, like air, water, or glass, it slows down. This slowing down is quantified by a property called the refractive index, n. For example, light travels slightly slower in air and significantly slower in water or glass. We'll see why this slowing down is so important when we discuss refraction later.
Let's continue with the wave nature of light. A fundamental formula connects three key properties: the speed of light, c, its frequency, f, and its wavelength, lambda. The relationship is simple. Speed equals frequency times wavelength, or f lambda equals c. This means that for light, which has a fixed speed in a given material, frequency and wavelength are inversely related. A color with a longer wavelength has a lower frequency, and vice versa. Speaking of color and wavelength, the different colors we see are defined by their specific wavelengths. In optics, we often use a very small unit called the angstrom to measure these. Here are the approximate wavelengths for the main colors of the visible spectrum, from violet with the shortest wavelength to red with the longest. As detailed in the figure, violet light has a wavelength around 4,500 angstroms, and red is about 6,400 angstroms. This range is what constitutes the visible light we will be focusing on in aircraft systems. Moving on from the nature of light, let's explore its behavior when it encounters a surface. This brings us to the principle of reflection. Reflection is defined as the change in direction of a light wave when it hits a boundary between two different media, causing it to bounce back into the medium it came from. The clean, mirror-like reflection we are most familiar with is called specular reflection. This happens on very smooth surfaces, whether they block light entirely, like a metal mirror, or allow it to pass through, like glass or water. You can see a perfect example of this in the figure. The fundamental rule governing this behavior is the law of reflection. To state it, we first need a reference line called the normal, which is an imaginary line drawn perpendicular to the surface at the exact point where the light hits it. The angle between the incoming light ray and this normal is called the angle of incidence, or theta I. The angle between the reflected ray and the normal is the angle of reflection, or theta r. The law is simple and absolute. Theta I always equals theta r. To formalize the laws of reflection, we already know the first and most important one: the angles are equal. But there are two more complementary laws. Second, the incident ray, the reflected ray, and the normal line all exist in the same flat plane. Think of it like a sheet of paper. All three lines lie flat on that sheet. Third, the reflected ray and the incident ray are always on opposite sides of that normal line. Reflection can occur from two main types of surfaces. The first is a plane surface, like your standard flat bathroom mirror. This type produces a predictable, straightforward mirror image. The second type is a curved surface. When light reflects off a curve, the laws of reflection still apply at every single point, but the overall effect is different. The curvature causes the reflected light rays to converge or diverge, which can magnify or shrink the image you see. This leads us to the two main kinds of curved mirrors used in practical applications. Now, let's look at the two types of spherical curved mirrors and their crucial applications, especially relevant for understanding certain aircraft instruments or inspection tools. First, the convex mirror. This mirror bulges outward like the back of a spoon. When light hits it, the rays are reflected outward or diverged. This creates an image that is demagnified. Everything looks smaller. However, this trade-off gives you a much wider field of view. That's precisely why they're used as the passenger side rear view mirror in cars to minimize blind spots. Second, the concave mirror. This mirror curves inward like the bowl of a spoon. It reflects light inward, focusing the rays. The image it produces can be magnified, but its exact size and orientation depend on how far the object is from the mirror's surface. We use concave mirrors where magnification is needed, such as in astronomical telescopes to gather light from stars, or in makeup and shaving mirrors to get a close, detailed view. This understanding of how light reflects from different surfaces is fundamental before we see what happens when light doesn't bounce back, but instead passes through a material, which is our next topic, refraction.
The bending of light during refraction is not random. It is precisely predictable by a fundamental formula called Snell's law. Snell's law mathematically relates the angles and the refractive indices of the two materials. It is commonly written as n1 sine of theta 1 equals n2 sine of theta 2. Here, n1 is the refractive index of the first medium, where the light starts, and theta 1 is the angle of incidence. n2 is the refractive index of the second medium, and theta 2 is the angle of refraction. Both angles are always measured from the normal line. This equation allows engineers to calculate exactly how much a light ray will bend. This precise control over the path of light is what makes optical lenses possible. By shaping glass or other transparent materials into curves, we use refraction to focus, magnify, or disperse light rays on demand, leading to essential devices like eyeglasses, camera lenses, and aircraft instruments. In our next session, we will dive into those very lenses to see how they apply the principles of refraction. Building directly on our knowledge of refraction, we now come to one of its most important applications, lenses. A lens is essentially any transparent device that uses refraction to bend and control light. Its primary purpose is to make light useful, like focusing the image of this test precisely onto your retina if you wear glasses. Two main factors determine how a lens behaves: the material it's made from, which defines its refractive index, and its physical shape or curvature. You can see the fundamental shapes in the figure. Lenses are classified in several ways. A simple lens uses a single piece of material.
To achieve sharper, clearer focus and correct distortions known as aberrations, we use compound lenses, which are stacks of simple lenses. Similar to mirrors, the most common basic shapes are spherical. A convex lens, thicker in the center, bends light inward to converge it. A concave lens, thinner in the center, spreads light outward to diverge it. Modern technology also produces aspheric lenses with non-spherical curves for even higher precision in complex optical systems. We now move to a transformative application of light in modern aircraft, fiber optics. This is the technology of guiding light through incredibly thin, flexible strands of glass or plastic called optical fibers. The principle is elegant. Electrical data signals are first converted into pulses of light. These light pulses then travel down the fiber at, well, the speed of light, to be converted back into electrical data at the other end. This method offers phenomenal advantages that are critical in aviation systems. First, it provides massive bandwidth, allowing huge amounts of data to be sent rapidly. Second, optical fibers are very lightweight, which is always a key design goal in aircraft. Perhaps most importantly, they are completely immune to electromagnetic interference, EMI. This means signals won't be corrupted by the powerful electrical noise generated by engines, radars, or other systems, ensuring reliable data transmission. You can see a conceptual overview of this system in the figure. To achieve this performance, the physical construction of the fiber optic cable is crucial. Let's look at the layers, moving from the inside out. At the heart is the core, the ultra-pure glass channel where light travels. Surrounding it is the cladding, a layer of glass with a lower refractive index. This difference in refractive index is what traps the light inside the core through a principle called total internal reflection, which we'll discuss later. These optical components are fragile, so they are coated with a tough buffer layer for basic protection and strength. In cables, multiple fibers are bundled together. To prevent light leaking from one fiber from interfering with its neighbor, light-absorbing material is often placed between them. Finally, the cable gets an outer jacket and often strength members like glass yarns. These protect against physical damage, including from pests like rodents, and provide tensile strength. A vital rule for technicians is respecting the minimum bend radius, usually no tighter than about 30 millimeters. Bending the cable more sharply causes severe signal loss and can permanently damage the fibers. This is a key point during installation in an aircraft's tight spaces. Now, let's delve into how light actually travels down a fiber. This is defined by its mode, and there are two fundamental types: single-mode fiber and multi-mode fiber. Single-mode fiber has an extremely thin core, less than about 10 times the wavelength of the light it carries. This tiny core forces the light to travel in essentially a single straight path, or a single mode. Think of it as a single-lane highway for light. It carries one signal at a time and is optimized for light in the near-infrared spectrum. This design is key for very long-distance, high-capacity data links, like those between continents. In contrast, multi-mode fiber has a much larger core. This allows multiple rays of light to travel simultaneously, each at a slightly different angle, like a multi-lane highway. Each light pulse can carry its own piece of data. This is perfectly illustrated in the figure, which shows the single straight path in SMF versus the multiple bouncing paths in MMF. How does the fiber keep these light signals contained? The answer lies in a principle we've touched on: total internal reflection. For a light ray to be guided, it must strike the boundary between the core and the cladding at an angle greater than a specific value called the critical angle. If it does, it is perfectly reflected back into the core. However, if the angle is too shallow, less than the critical angle, the light refracts into the cladding and is lost, as shown in the figure. This is a key design parameter. No system is perfect, and some light is always lost as it travels. This loss is called attenuation or transmission loss. It's caused by imperfections that scatter light and by the material itself absorbing a tiny amount of energy. Attenuation is the main enemy of long-distance fiber optic communication, setting a limit on how far a signal can go before it needs to be amplified. The engineering achievement here is astounding. Modern single-mode fibers are so clear that if ocean water had the same level of attenuation, you could see clearly all the way down to the bottom of the Mariana Trench, over 36,000 feet deep. This incredible clarity is what makes global telecommunications possible. We've seen how light travels through the fiber. Now, how do we connect these fibers to equipment or to each other? We start with termination using connectors. An optical fiber connector provides a removable link between a fiber and a device like a sensor or computer. The goal is to align the microscopic fiber cores perfectly to minimize signal loss or attenuation and prevent light reflections. Standard connectors achieve this through physical contact polish, where the mating surfaces are angled so they touch precisely at the core. Installing one is a meticulous process. The fiber is stripped, inserted into the connector, glued in place, and then its end is polished to an optical quality mirror finish. For single-mode fibers, an advanced polish creates a slight curve, ensuring contact only at the very center of the core. This sacrifices a tiny bit more light, but dramatically reduces harmful back reflections, which is critical for high-speed data systems. To join two fibers end-to-end, we use splicing. There are two main techniques. The industry standard for a permanent, high-performance joint is fusion splicing. Think of it as welding for glass. The fiber ends are stripped, perfectly cleaved, aligned with micrometric precision inside a splicer machine, and then fused together using a tiny electric arc. The machine then measures the splice loss, which is typically an incredibly low 0.1 decibels or less. This is the method used for long-haul and critical aircraft data buses. For quicker jobs or temporary fixes, mechanical splicing is used. Here, the prepared fiber ends are aligned and clamped inside a precision sleeve, often using a special optical gel to improve light transmission across the gap. While faster, these splices have higher signal loss and are less physically robust than a fused joint, making them unsuitable for permanent installations in harsh environments. Where do we see this technology in aviation? It's already here and growing. In military aviation, fiber optics have long been used for heads-up displays, or HUDs, providing a robust, interference-free link to project vital information onto the pilot's windshield, as shown in the figure. In commercial aviation, aircraft like the Boeing 777 use fiber optics for non-critical but data-heavy systems like the in-flight entertainment network, where its huge bandwidth shines. The promise is to expand its use to more critical systems. Why this push? The advantages are overwhelming for aircraft design. Massive bandwidth in a lightweight cable, complete immunity to the intense electromagnetic noise in an aircraft, enhanced security as signals don't leak out, and inherent electrical safety with no risk of sparks or short circuits.
In system performance, fibers offer lower signal loss over distance, resulting in fewer data errors. Unlike electrical cables, light in adjacent fibers doesn't interact, so there's no crosstalk. Second, for security and safety, tapping a fiber optic line without detection is very difficult because light doesn't radiate out. The cables are non-conductive, providing perfect electrical isolation. They don't need a common ground and eliminate risks of sparks or short circuits, a critical safety feature in fuel-rich environments. Finally, the size, weight, and environmental benefits are key. Fiber cables are smaller and lighter than equivalent copper cables, while being completely immune to all forms of electromagnetic and radio interference. In essence, fiber optics delivers reliable, high-speed data in a lightweight, secure, and supremely tough package, qualities that define modern avionics. To complete our understanding, let's look at the fiber optic data link. This is the entire system that makes practical use of the fiber. A data link has three key parts. First, the transmitter. It takes in electrical data, and its drive circuit uses a light source, typically an LED or a laser diode, to convert that data into pulses of light. A high-quality connector is crucial here to launch that light efficiently into the fiber with minimal loss. The light travels through the optical fiber itself, which is our transmission medium. At the far end, a receiver uses a photodetector to convert the light pulses back into electrical signals for the avionics computer or display to use. Another precision connector is needed here. In aviation, the adoption of fiber optics has been balanced. On one hand, the cost and handling challenges of connectors have been a limitation. On the other, the irresistible advantages of huge bandwidth, light weight, and total immunity to electromagnetic interference are powerful drivers for its development. The future is promising. While hybrid systems with copper will remain, ongoing research aims to overcome current shortcomings. As shown in the figure, we may someday see fiber optic data links controlling primary flight systems like landing gear and flight controls, making aircraft faster, lighter, and more reliable. Let's take a moment to review the comprehensive ground we've covered together. We began by exploring the fundamental nature of light itself, understanding it as a wave and part of the electromagnetic spectrum. We then studied its core behaviors: reflection, where light bounces off surfaces following precise laws, and refraction, where it bends when passing through materials, a principle mathematically defined by Snell's law. This understanding of refraction led us directly to lenses, the engineered components that focus and direct light for countless applications. Finally, we immersed ourselves in one of the most transformative technologies in modern aviation, fiber optics. We broke down its cable construction, the difference between single-mode and multi-mode transmission, the critical practices of termination and splicing, and we saw how it all integrates into a complete data link system. And that brings us to the end of this submodule. Now, let's warm up with a few questions to review what we've learned.
Now let's get started with question 1. What is the refractive index of a material defined as? A, the speed of light in the material divided by the speed of light in a vacuum. B, the wavelength of light in a vacuum divided by its wavelength in the material. C, the speed of light in a vacuum divided by the speed of light in the material. The correct answer is C, the speed of light in a vacuum divided by the speed of light in the material. As we mentioned, the refractive index, denoted as N, is a measure of how much light slows down when passing through a material. It is mathematically defined as N equals C divided by V, where C is the constant speed of light in a vacuum and V is the slower speed of light in that specific material. Therefore, a higher refractive index indicates a greater reduction in speed. Option A is the inverse of the correct definition. Option B describes a related effect but defines the refractive index incorrectly. Question 2. According to the laws of reflection, which of the following statements is always true? A. The reflected ray and the incident ray are on the same side of the normal. B. the angle of incidence is greater than the angle of reflection for convex mirrors. C. The angle of incidence is equal to the angle of reflection. The correct answer is C. The angle of incidence is equal to the angle of reflection. This is the fundamental universal law of reflection. It holds true regardless of whether the reflecting surface is flat or curved, specular or diffuse. The angles are always measured between the rays and the normal, the perpendicular line drawn at the point of incidence. Option A is incorrect. A specific law states that the incident ray and the reflected ray are on opposite sides of the normal. Option B is also false. The equality of angles, theta I equals theta R, applies to all mirror types, including convex ones. The demagnification in a convex mirror is due to its curvature, not a change in this basic law. Question 3. When light passes from air into glass at an angle, why does it bend towards the normal? A. Its frequency decreases. B. Its wavelength shortens and its speed decreases. C. Its wavelength increases and its speed increases. The correct answer is B. Its wavelength shortens and its speed decreases. Refraction occurs precisely because the speed of light changes when it enters a new medium. As stated in the text, when light enters a denser, slower medium like glass, its speed decreases. Its frequency, however, is fixed and cannot change. Therefore, to satisfy the wave equation, speed equals frequency times wavelength, the wavelength must shorten. This combined effect of slowing down and shortening wavelength causes the light ray to bend towards the normal line. Options A and C describe changes opposite to what actually occurs. Question 4. Light travels from water, refractive index N1 equals 1.33, into an unknown material. The angle of incidence in water is 30 degrees, and the angle of refraction in the material is measured to be 25 degrees. Using Snell's law, what is the refractive index N2 of the unknown material? Use sine 30 degrees equals 0.5, sine 25 degrees approximately 0.42. A. Approximately 1.58. B. Approximately 1.12. C. Approximately 1.90. The correct answer is A. Approximately 1.58. We use Snell's law in its common form. N1 sine of theta 1 equals N2 sine of theta 2. We plug in the known values. N1 is 1.33 for water. Sine of theta 1 is sine of 30 degrees equals 0.5. Sine of theta 2 is sine of 25 degrees, approximately 0.42. So the equation becomes 1.33 times 0.5 equals N2 times 0.42. This calculates to 0.665 equals N2 times 0.42. To find N2, we divide both sides by 0.42. N2 equals 0.665 divided by 0.42. Performing this division gives us N2 approximately 1.58. This result means the unknown material is optically denser than water, as light bent towards the normal, from 30 degrees to a smaller 25-degree angle, indicating a slower speed of light in that material. Question 5. What is the primary purpose of a compound lens compared to a simple lens? A. To allow the lens to refract non-visible electromagnetic waves. B. To refine the focus and eliminate optical aberrations. C. To change the basic spherical shape into an aspherical one. The correct answer is B. To refine the focus and eliminate optical aberrations. As we mentioned earlier, a simple lens causes a single refraction, while a compound lens is constructed from multiple simple lenses. The key advantage of this design, as stated, is to refine the focus and eliminate aberrations. An aberration is a defect where light rays fail to converge at a single sharp point, leading to a blurred or distorted image. Compound lenses correct for these imperfections. While option A describes a capability of some lenses, it is not the defining purpose of a compound design. Option C describes a technological advancement, aspheric lenses, but is a separate concept from the fundamental purpose of combining multiple lenses into a compound system.
Question 6. What is the primary purpose of the buffer and jacket layers in a fiber optic cable? A. To increase the speed of light transmission through the fiber core. B. To provide mechanical strength and protection without affecting optical properties. C. To prevent signal loss by absorbing leaked light between adjacent fibers. The correct answer is B. To provide mechanical strength and protection without affecting optical properties. As we have learned, a fiber's cladding is coated with a tough buffer layer, which may be further surrounded by a jacket. These layers are explicitly stated to add strength to the fiber, but do not contribute to its optical properties. Their role is purely mechanical, to protect the delicate glass core from physical damage, moisture, and environmental hazards like rodents or insects, ensuring the cable is durable and flexible enough for installation. Option A is incorrect. The speed of light in the core is determined by its refractive index, not the outer layers. Option C describes the function of a separate, light-absorbing material, sometimes placed between fibers in a bundle, not the primary role of the buffer and jacket for an individual fiber.
Question 7. What is the key factor that determines whether a light ray is completely reflected within the core of a multi-mode optical fiber? A. The color, wavelength, of the light pulse. B. The diameter of the fiber's core. C. The angle at which the ray meets the core cladding boundary. The correct answer is C. The angle at which the ray meets the core cladding boundary. This is a direct application of the principle of total internal reflection, which is the operating mechanism for all optical fibers. As we mentioned earlier, rays that reflect from the cladding at angles greater than the critical angle are completely reflected. These rays carry the signal along the fiber. Conversely, rays that meet the boundary at a shallower angle, less than the critical angle, are refracted into the cladding and are lost. While core diameter, B, distinguishes single-mode from multi-mode fiber, it does not dictate the reflection condition for an individual ray. The wavelength, A, influences the critical angle, but the decisive factor for any given ray is its incident angle relative to that boundary.
Question 8. What is the primary purpose of polishing the fiber ends with a slight curvature in a PC connector for single-mode fibers? A. To increase the adhesive surface area for a stronger bond. B. To ensure the mated connectors touch only at their cores, reducing back reflection. C. To allow for easier alignment during the mechanical splicing process. The correct answer is B. To ensure the mated connectors touch only at their cores, reducing back reflection. As we explained, for single-mode fiber, the ends are polished with a slight, precise curvature. This intentional design creates a connection where the two fiber cores are in direct physical contact, but the surrounding cladding areas are not. This minimizes the air gap at the critical core interface, which in turn greatly reduces back reflection. The light that does reflect from the angled surfaces is directed out of the fiber core and is lost, preventing it from traveling back up the fiber and interfering with the signal source. Options A and C describe processes related to installation and splicing, not the specific optical goal of the PC polish.
Question 9. When performing an arc fusion splice, what is the purpose of the initial, small spark emitted by the splicer? A. To preheat the fiber ends and prepare them for fusion. B. To measure the initial optical loss before the splice is made. C. To burn off dust and moisture from the cleaved fiber ends. The correct answer is C. To burn off dust and moisture from the cleaved fiber ends. The fusion splicing process is highly sensitive to contamination. Before the permanent fusion spark is applied, the splicer emits a smaller preliminary spark. As we described this step earlier, the splicer then emits a small spark at the gap to burn off dust and moisture.
This cleaning step is crucial for achieving a low-loss, high-strength splice. Option A describes a general effect, but not the primary intended purpose. Option B describes the final measurement step, which occurs after the splice is completed, not the function of the initial spark. That's all for today's lesson. If you found this video helpful, please give it a thumbs up and consider subscribing to AirWise Academy for more aviation knowledge. We'd love to hear your thoughts or questions in the comments below. Turn on notifications so you won't miss our upcoming videos. Until next time, blue skies and happy learning!